Let's do an example with this real fast. It's not difficult. Okay, example. And then we'll get to the third law and we'll be done. Example. Let's say Akita, Sam, and Suki. These are all dogs. Pull on the sled as shown. And we got our sled down here. I won't take too much time on this drawing, though I want to. I love taking time with my drawings. But we'll have one dog pulling over here, another dog pulling here, right? There we go. And we'll make this dog maybe, it's a tiny little dachshund, right? It's got the floppy ears. I don't know, you can name them in your problem, right? And then we'll have another one pulling this way. This is like a Great Dane right here. Looks like a Nubis. I don't know about a Great Dane. There we go. We got all these dogs pulling different directions. This one's pulling with a vector of, let's say, 500 newtons. Sounds reasonable. This dachshund, let's face it, it's not pulling with very much. Let's say 100 newtons. This guy right here, the bell of the ball, 1,000 newtons right here. Guy says, forget you too. All right, let's go ahead and solve. If the mass of this sled is, I don't know, let's just go 10 kilograms, keep our math easy, right? Let's find acceleration. Find acceleration. Cool. So how would I do this problem? I wish I could tell you this is as easy as our FNet problems will be in AP Physics, but that is not the case. This is very much an introduction problem. Here's something I will remind you of. In vector addition, I always call the dominant direction positive. So I know the dominant direction is left, and normally we say in kinematics that left is negative. I understand that. But when I'm doing vector addition, kind of go away from that, and I say, nope, let's just make the dominant direction the positive direction. So what I would do here, FNet, what I actually would do, I would solve for acceleration first, right? That's what I'm looking for. So I'd have A equals FNet over M. Yeah, oops, too many. There we go. A equals, now what is FNet? It's 1,000 newtons minus 100 minus 500, all divided by the mass of 10 kilograms. That is the unit we're going to use most of the time, and that is the unit you have to convert to. Let's say your problem gives you grams, you got to convert to kilograms. So you want to stay in the MKS system this year. M is meters, K is kilograms, S is seconds. So those are the typical units we use for length, for mass, and for time. Okay, back to this. What do we have up top here? We have 1,000 minus 600, right? So we would have 400 newtons to the left, all over 10 kilograms. Pretty straightforward math, right? We have 40 meters per second squared. Now your question is, how did you get to meters per second squared? We'll get there. Okay, I'm going to tell you that in just a second. But that's our answer, right? 40. That's a ridiculously fast acceleration. I would not want to be on this sled, right? You are getting yanked the other direction pretty quickly if you're starting from rest, right? I mean, this could be a problem with, never mind, let's not introduce more stuff, all right? So that's the math. Now I have people ask me all the time, well, hold on a second, why did you subtract and subtract? Aren't these two together 600, right? Shouldn't you add those two? You could. But then you would very specifically need to do what I'm about to show you. You'd have to say minus, because agreed, these two are opposite from that 1,000. That's why I'm putting minus. They're acting opposite from 1,000. Minus, the parentheses need to come into play, 100 newtons plus 500 newtons. What would you get? You get 600, but you'd have a negative there, making it minus 600, right? So you could do that. If you'd rather do that, you will see me do what I did all the time. Okay. So that is the idea. Now, quick unit analysis so I can finally get to that third law. Newton What is a Newton? A Newton, by definition, maybe I'll write this over here. Hey, a little side note to myself. A Newton is equivalent to a kilogram meter per second squared. Well, that sounds like magic. That sounds convenient. Not really. Look at F net. What is force? Force is a mass times an acceleration. What's the unit of mass? Kilogram. What's the unit of acceleration? Meters per second squared. So it makes sense that a Newton, which force is measured in newtons, should be a kilogram meter per second squared. All right. So looking at my UA over here, what is really a Newton? It is a kilogram meter per second squared, all divided by a kilogram. And what happens to your 2 kilograms? They cross out. You're left with your meters per second squared. Awesome. Let's get to that third law. We'll make it, I'll try to make it quick, guys. Try. You know this one. I'll get you started. For every action, there is, and you should all be saying, an equal and opposite reaction. That is the third law. The third law states, for every action, there is an equal and opposite reaction. No, we're saying action in what your 8th grade teacher meant, what your 4th grade teacher meant. Whenever you heard this before in your science education, they meant force if they didn't tell you that. An action is a force. There's an equal and opposite reaction. That's a force. And while this is easy to say, it sounds poetic, it has implications that if I asked you a question without teaching you this lesson, you'd probably get the wrong answer. You saw me hit that pen across the room a second ago. Let's say I hit that pen with 1,000 newtons. I hit the pen with 1,000 newtons. You'd be like, okay, yeah, that makes sense. It went flying across the room. But what is the other side of the coin? I hit it, and what did it do to me? Didn't it strike me at the same time? And if this law is true, it hit me with how many newtons? 1,000 newtons. And that's where you're like, what are you talking about? Your hand's fine. Your hand didn't budge. In fact, your hand went right through that thing and made it go. So how is your hand hit by 1,000 newtons? It didn't seem affected at all, right? So let's get to the bottom of that seemingly paradoxical situation, okay? In fact, we are going to use a pen. There's my pen, right? Pen. Maybe there, pen there, okay. And here comes hand. Hand is coming in, and I'm going to quickly do this. Oh my gosh, look at this gigantic hand. This hand that could build houses, form nations, tear down walls, I'm sure. Look at that hand. It's massive influence. Yes. Wouldn't this be more fun in person? Okay. So it's coming in. There goes my hand. It's about to hit that pen. That pen's stationary, right? And my hand hits that thing, and I'm going to put a force on the pen. Okay, put a big old force on that pen. And I'm going to say F, H, P. No, you know what? Let's not even hand on pen. Right? Force of the hand on the pen. But if this law is true, and it is, then there is an equal and opposite force on my hand, and I'm going to draw that vector the same length as that one, and that is the force of the pen on the hand. And I'm telling you right now, they're equal to each other. They're absolutely equal. If you wanted to throw in that value of 1,000 helps you, that's fine. I'm not going to. I'm going to stay general just like this, okay? Coming down here, I would say FHP equals FPH. I think you can see why I wrote the letters in the order that I did, right? I hope so. So here is where it makes sense. Here's where it absolutely makes sense. What are these unbalanced forces equal to? Each one of these unbalanced forces is equal to mass times acceleration. We just learned that in the second law. And by the way, I don't think I made enough of a point of that because I got busy talking about the example, right? This is the second law. simply stated, acceleration is inversely proportional to mass and directly proportional to the unbalanced force. I'll say it again. Acceleration is inversely proportional to mass and directly proportional to the unbalanced force. You can write that verbal statement if you want, but really whenever I say what's the second law, I want you to tell me that equation, F net equals ma. That is the second law. Okay, so back to our in-hand example and the end of these notes. The pen's mass is incredibly tiny. So FHP would equal the mass of the pen. Symbolically, I'm going to draw a little mass M. And you saw what happened to that pen, or you didn't because it was so fast. What happened? That pen had a tremendous acceleration. Little mass times a huge acceleration is equal to what? FHP. Force is equal to mass times acceleration. But what about the other side of this equation? The force of the pen on the hand. Well, look at the mass of that hand. That hand is incredibly massive in comparison to the pen. Incredibly massive. Mass times. Now here's the part where you have to think a little. I hit that pen, my hand is coming through, and it has an acceleration because I'm generating a force, right, with my musculature, right? It's coming through. And when it hits the pen, is there a tiny, tiny deceleration in the hand as it hits the pen? Yes. So if my hand's coming through, like, let's say with like, I don't know, 20 meters per second squared of acceleration, right? There is a tiny drop in that 20. Maybe it's now 19.9999999 meters per second squared. But there's a tiny deceleration, a tiny acceleration that happens for the hand. And I say deceleration because it slows down a little bit, right? So here's how it can make sense that if I hit a pen with 1,000 newtons, it hits me with 1,000 newtons. Because it's not really the force. It's not really the force itself that we should be thinking about. It's the mass times the acceleration that we should be thinking about, right? You have an incredibly small mass, and what happens to make this equation work? It gets an incredibly big acceleration, and the very big mass gets a very tiny deceleration, such that, let's just make up a number here, 1 times 1,000, right? A mass of 1 times 1,000 acceleration would equal a mass of 1,000 times a deceleration of 1. Okay, and that's how we can make sense of this. So as morbid as it is, we always think about forces as being the things that kill or the things that really hurt somebody, right? Say someone falls from a second story. We're not going to, kill anyone in our example. They fall from a second story, they break their legs, it's no good, right? Is it the force that killed them? I mean, you could argue it is, but really it's that very fast deceleration their body goes through. I mean, it's a tremendously big deceleration in my example of someone falling off like a second story, right? And that quick deceleration is just too much for their skeletal muscular system to handle, and things break and organ systems get messed up and it's no good, right? But it's that really fast acceleration or deceleration that can hurt you. These notes are done. I hope it all makes sense. We'll be talking soon on more force stuff. Have a great day.